Hello everyone, my name is Tian Geng from Seoul National University. I will present our work titled Star Spatial-temporal prediction of air quality using a multimodal approach. I will divide my talk into 6 sessions as follows. First, I will introduce the problem and the research literature. Then I will present how to collect the data. Next, I describe our proposed methods and our experimental results. Finally, I will wrap up and show some potential future directions. At the moment, COVID-19 will kill nearly 700,000 people worldwide, and COVID vaccines are our main concerns. However, air pollution kills roughly 7 million people worldwide every year. It is a pressing issue for many large cities due to the rapid urbanization along with the economic activities. An accurate citywide air quality prediction model is necessary to protect human health and government regulation. Air quality changes in both time and space dimension and is impacted by many factors such as transportation, coal power plant, and dust activities or economic activity, as you can see on the right figure. Many cities set up the monitoring station across the location to measure air quality levels, including gaseous pollutants and particulate matter. From these sources of data, we can consider the air quality prediction as a time series problem that predicts air quality levels of stations. Many researchers have approached this way. However, the performance usually depends on the feature extraction processes. Spatial-temporal prediction is a promising direction that solves the problem, since it proved to be an appropriate approach to urban problems. However, it's usually hard to collect enough data of all critical factors and assess the impact of them on the main problems such as the air quality. Spatial-temporal prediction has been pre- prevalent in urban problems such as taxi demand prediction or precipitation prediction. In the air quality prediction domain, CNN LSTM or convolutional LSTM or graph LSTM are well-known approaches. Zhu Zhang's research group is the most celebrated in this air quality prediction with many findings. Most models are based on the feature extraction algorithm and difficult to scale up. Therefore, we propose a spatial-temporal prediction of air quality using a multiple modal approach. We try to solve the lack of data and assess the correlation between the critical factors and the air quality levels. First, we will use two datasets for the research, as you can see here. China 1 year dataset is public data, while our soon 5 year dataset is our collected one. We collected soon dataset from public resources as listed on the right side. The dataset includes air pollution data from Seoul and some cities in China, meteorology, and additional information such as holiday information of corresponding areas. Here is the flow of our data collection process. First, we crawl HTML pages from the aforementioned website, and we then remove redundant data, interpolate the missing data. Next, we fix the timestamp alignment of the different datasets and normalize them. Finally, we split the data into train depth and test set. For example, we saw dataset with 3 years, a half year, and 1 year for train depth and test set. Now, let me explain how the data are processed in our model to make the prediction. Our model follows the concept of encoder and decoder framework. I will move from the left to the right and unveil each part of the model. First, our model takes into account 4 data sources and denotes them as you can see here. The detailed attributes are listed as follows. I stands for the air pollution data of investigated areas such as Seoul. M stands for the meteorology. D is the additional information such as the daytime or the end. Stand for the neighboring area. pollution data. Next, a second construction includes three subparts for learning historical spatio-temporal relationship of critical factors in this investigated area, future weather changes, and the impact of neighboring area air pollution on the investigated one. Specifically, as the collected historical data are organized as the literates, we cannot collect the geological with latitude and longitude data. We transform them into the images to automatically model the spatial relationship among areas. The model feeds these images into CNN layers that follow to output a sequence of vectors. All three subparts share the same LSTM structure that capture the temporal changes. Finally, the encoder context is provided by an attention mechanism. Given the encoder context, the decoder starts generating the predictions. The output of the current step is fed into the next step as similar to a language modeling network. Notably, the CNNs of the decoder are transpose CNN, not similar to the encoder CNN. The model averaged pixel of an area corresponding to a district to be each prediction output. We perform many experiments to prove our hypothesis and compare our model performance with its baselines. We use Adam optimizer with mean square error and loss function. We evaluate the result using mean absolute error. We normalize the data into the range 0 and 1 using mean mark normalization. Practically, the length of sequence construction is set at 24 and 48 for SC and NC modules, and the length of WC is the same as the prediction length. Our work focuses on not only the short-term air quality prediction, but also the long-term variation for up to 7 days. I think this is important to us since we want to know the long-term air pollution as well as the short-term. For example, when we plan for a busy trips, first we compare our model with baselines on PM2.5 and PM10 prediction and show that our model outperforms them, especially in daily prediction. Next, we test the generalization capability of our model on China 1G dataset and see that our model significantly improves the results compared to the previous methods. Specifically, we observed that if we pre-train the model a few epochs in the Seoul dataset, then fine-tune in the China dataset with only 1 year, we can get better performance. Finally, we assess the impact of the critical factors on the future air quality levels. As many environmental papers pointed out that the dispersion and the formation of particulate matters depend on time, wind speed, precipitation, and humidity. Based on our findings, PM2.5 is more sensitive to the ambient conditions such as the meteorology, other air pollutants, and transboundary air pollution than the PM10. Furthermore, both particulate matters tend to change slowly in short term while they fluctuate significantly in the long term. Specifically, in zone area, transboundaries and the neighboring countries' air pollution significantly impacts on the variation of PM2.5 levels, especially under some specific seasonal conditions and weather conditions. That's all. Let me briefly conclude our contribution and discuss the future works. We propose a multimodal approach for predicting the short to long-term air quality levels. We transform the observational data into heat map images for better spatial relation representation. Our model outperforms baseline, especially in daily prediction. In the future, we will investigate the sudden change point when the air quality level abruptly turns from good to bad or bad to good. Next, transfer learning methods for similar problem may be considered. Finally, we can build IoT platform for urban computing problems. Thank you very much for listening.